Welcome everyone. Myself Dr. Ruchira Goel from Department of Applied Science and Humanities, Ajay Kumar Garg, Engineering College, Ghaziabad. Today I will be discussing Mathematics 4 code KAS 302/402 partial differential equations. My contents which I will be discussing are partial differential equation of higher order with constant coefficients. In particular, in this particular topic, I will be considering homogeneous partial differential equations. Now, first of all, we are considering linear homogeneous partial differential equation with constant coefficient. What is the meaning of this term linear? We can see that here an equation is written, and this equation number 1 which is written over here, the terms written over here are all having the power as 1. Derivative of z with respect to x is taken n times, but the power of this derivative is 1. Then again in the next term, this term is also having power as 1. Then the next term, and so on till the last term, all are having power as 1. So if the power of the derivative we are considering is 1, that means the equation is linear in nature, and it is homogeneous, because we can see that the derivative which is being considered here in the first term, we are having derivative of z with respect to x n times. So this is giving us del n z by del xn. So in the second term also we are taking derivative of z with respect to x and y, and with respect to x we are taking derivative n minus 1 times, and with respect to y we are taking derivative 1 time. So n minus 1 plus 1, this total comes to n. So again the order of the derivative here is n. And similarly in the last term we are having derivative of z with respect to y n times, and with respect to x we are having 0 times. So that means the total derivative value here also comes out to be n. So that means all the terms are being taken derivative n times. So now if we have a look on the content partial differential equation, partial because here we are having two variables x and y. So x and y both are independent variables and z is a dependent variable. So z is dependent and x and y are independent. So there are two variables which are independent. So that's why this is a partial differential equation. Now we have understood why it is a homogeneous linear partial differential equation of order n. Constant coefficients, this term means that all the ai's, that is a0, a1 till an, all are constant. That's why this is a constant partial differential equation. Now what we will do, we will put del by del x as d, we will substitute del by del y as d dash, and therefore the given equation 1 can be written as a0 d to the power n plus a1 d to the power n minus 1 d dash plus terms up to an d dash n applied to z equal to fxy. Now this fxy is a function of x and y both. So in other words, we can write this as function of dd dash applied to z gives us some is equal to some function of x and y. Now how we will discuss the rules for finding the complementary function. Now the rules for finding complementary function we will consider as the first step as we will substitute d equal to m, d dash equal to 1 to find the auxiliary equation. To find the auxiliary equation, if we substitute d as m and d dash as 1, the equation which was in the previous slide, this equation will be convert into a function of m and 1. So in the second step, the roots of this equation can be provided as m1, m2, mn. We can find these values of m1, m2, mn. And if the now there are two cases. If the roots of the auxiliary equation are real or imaginary or irrational, but they should be different. This is to be looked up, that they should be all different. Then suppose we consider them as m1, m2 up to mn. So we have the CF to be written as function of y plus m1x, function of y plus m2x plus function of y plus mnx. And there is another situation whereby in case 2, if the roots are equal. If the roots are equal, then all the roots which are equal, we will consider them as, suppose, m. So in this situation, CF will be given by a function of y plus mx plus this x is something which is to be noted that it has to be placed before function of y plus mx written again. And we will keep proceeding till we get the same number of terms as are the equal number of roots. That means if we have two roots which are equal, say m1 and m2, then this CF will have two terms, this and this. But if suppose there is one more root which is equal to m, so in that case we will have one more term which will be given by x square, which will be given by x square function of y plus mx. So this is the situation if we have three roots which are equal, and we will keep proceeding like this for all the equal roots. So this is the situation. This will be our CF provided we have three roots m equal to m1, m2, m3, like this. So we have understood this concept, but there is something more to it. What is that? We have, suppose, instead of d to be replaced by m, we replace d dash by m and we replace d by 1. So in that situation, both cases will still occur, but the difference will be that instead of this CF, we will have CF in that situation to be written as case 1. In that situation, CF will be function of x plus m1y plus function of x plus m2y and plus function of x plus mny. And in the second case, when we have equal roots, so instead of the CF which is written over here, we will have the CF as CF equal to function of x plus my plus y times function of x plus my plus y to the power n function of x plus my. Now let us discuss few examples. So suppose we have to solve d cube minus 4d square d dash plus 3d dash square z equal to 0. Now we will put d equal to m and d dash equal to 1. So we will get the auxiliary equation as m cube minus 4m square plus 3m equal to 0. Its factors are given by m minus 1, m minus 3 equal to 0, which gives the value of m as 0, 1 and 3. These values are different, they are distinct. So hence CF will be CF will be given by let me correct it, this should be CF. So this will be given by function of y plus f2 function of y plus x, because here the value we are considering of m as 1 and here we are considering the value of m as 3. So function of y plus 3x, that means here we have f1y, that means this is actually f1 y plus 0x. So that's why this is f1y. This is the case when roots are distinct. But suppose we take another example where we have d square minus 4dd dash plus 4d dash square z applied to z equal to 0. In this case, when we substitute d by m and d dash by 1, we get auxiliary equation as m square minus 4m plus 4 equal to 0. So that gives us m minus 2 whole square equal to 0, and I get m equal to 2 comma 2, that means we get equal roots 2 comma 2. So 2 is an equal root 2 times. So CF will be given by function of y plus 2x plus x times function of y plus 2x, since the roots are equal. So this is from case 2. If we have the right hand side 0, then only we can write CF as the complete solution. So in above case, my complete solution will be the value of z also. So z will be equal to CF in this case, and in the second example also I will have z equal to the complementary function, since the right hand side of this equation is 0 and here also it is 0. But suppose this is not 0, in that case we need to actually find out the contribution of the right hand side function as well. So how we will proceed for that? So let us discuss rules for finding the particular integral. Particular integral is a solution we consider when we have the right hand side function as some function of x and y. Like we have already discussed in the previous slides that this right hand side can be some function of x, y. So we have already discussed this. So this is some function of x and y. In that situation we will find particular integral also. So to find particular integral, first case is when phi xy, that means we have the function on the right hand side as some function of ax plus by. So the right hand side is a function of ax plus by form, and in that case to find the particular integral of the equation f dd dash z equal to function of ax plus by, we need to look up that this f of ab must not be equal to 0. F of AB means when we replace d by a and d dash by b, we should not get the value of the function as 0. If it comes out to be 0, then this method will fail. So this method is applicable only when the function value is not equal to 0. So what is the process to find pi of such functions? We will replace d by a and d dash by b. So to get FAB, put ax plus by equal to u and integrate phi u. Now the question arises, how many times we need to integrate? So we will integrate it n times with respect to u. That means the order of the differential equation will decide how many times the integration of the function phi u has to be considered. If it is 2, the order is 2, you will integrate 2 times. If the order is 4, you will integrate 4 times. If the order is n, you will integrate n times. So this particular integral will be given by 1 upon f ab. This value will be some constant value after substituting ab. Integration symbol I have considered n times because function is being integrated n times with respect to u. And in the end, when you solve this function value, then replace u by ax plus by in the end, because u is something which we have considered and which should not be there in the first instance. So let us consider an example. Suppose we need to solve 2d square minus 5dd dash plus 2d dash square z equal to 24 into y minus x. Now as I can see on the right hand side, this 24 y minus x is actually 24 minus 1 into x plus 1 into y. So comparing it with ax plus by, I get a as minus 1 and b as 1. So first of all, since it is written, we have to solve. So auxiliary equation, we have to find the complementary function. So auxiliary equation is given by 2m square minus 5m plus 2 equal to 0. We have replaced d by m and d dash by 1. So d is replaced by m and d dash is replaced by 1. So we have 2m minus 1 and m minus 2 as the factors, which gives us m equal to 1 by 2 and 2, which are both distinct. Therefore, according to case 1 of complementary function, CF will be given by a function of y plus 1 by 2x. That means the first value of m we have considered here in this place, and then function of y plus 2x. So the second value of m is being considered with x. Now pi, to find pi, we need to substitute a and b. We need to substitute a and b where? In the left hand side function. That means my fdd dash was 2d square minus 5dd dash plus 2d dash square. So if I find FAB, that means f minus 1 comma 1, I will be having 2 into minus 1 square minus 5 into minus 1 into 1 plus 2 into 1 square, which turns out to be equal to 9. So f minus 1 comma 1 is non-zero, obviously this is not equal to 0, hence we can apply the first case of pi. That means we will find out 1 upon 2d square minus 5dd dash plus 2d dash square applied to 24y minus x, and after this 24 is constant, so 24 upon this substitution I have already shown you over here, that f of minus 1 comma 1 is placed, and this integration is taken 2 times, because I can see that the order of this equation fdd dash, this equation has order 2. So this equation has order 2, hence we have the integration taken 2 times, and instead of y minus x, this was my function, this y minus x was my phi ax plus by. So this will be replaced by phi u. So y minus x will be replaced by u, and this gives me integration of u 2 times with respect to u. So I get 4 by 9 u cube after integration, and this gives me, in place of u in the end I will again substitute u with y minus x. So this u is replaced again by y minus x. So this is my particular integral. Now the complete solution is given by, this is my z actually. So this will be given by complementary function plus particular integral, and hence I get function of y plus 1 by 2x plus function of y plus 2x and 4 by 9 times of y minus x whole cube as my complete solution. So in the first case we get this as our answer. Now we will proceed further. So coming to case second. In case second, we have a function of x, y, and it should be of the form x to the power m, y to the power n. That means we cannot have some addition in between, subtraction in between, or division. It means these powers should be of x and y. They either of the powers can be 0 also, but the function should be of this form only. Now let us consider an example. Suppose I have to solve del cube z by del x cube minus 2 times del cube z by del x square y as equal to 3x square y. Now if I have to solve this value, in that situation, first of all, since it is not in the operator form, I will replace del by del x by d, and I will replace del by del y by d dash. So I get the equation as d cube minus 2d square d dash, this is d dash, applied to z equal to 3x square y. So to write the auxiliary equation, I will replace d by m and d dash by 1. So I am having auxiliary equation as m cube minus 2m square equal to 0, which gives me m equal to 0, 0 and 2 as the roots. We can notice that there are as many roots as is the order of the equation which is given to us. That means the order of the equation was 3, so hence there are 3 roots. So 2 of them are equal, 1 is distinct. So we will have cases from both the complementary function. That means complementary function for equal roots will follow case 2, and for distinct root, that is root 2, we will follow the case 1. So the pattern is function of y plus x time function of y. This is corresponding to the root 0. Corresponding to root 2, we will have function of y plus 2x as the complementary function. Now pi, coming to pi, to find particular integral, what we will do, we will actually need to expand. So first of all, pi will be 1 upon d cube minus 2d square d dash applied to 3x square y. I will consider the expansion. We need to apply the binomial expansion. So I have taken this d cube common outside, and I am left with 1 minus 2 d dash, this d dash upon d applied to 3x square y. So this gives me 1 upon d cube, and this 1 minus 2 d dash upon d to the power minus 1 applied to 3x square y. If I have expansion of 1 minus x to the power minus 1, then I have 1 plus x square plus terms up to infinity. So this expansion, when I apply on this function, this 1 instead of x, I am having actually 1 minus 2d dash upon d. So I will be having 1 plus 2 d dash upon d plus 2 d dash upon d whole square and terms up to infinity, like this. So the terms will continue. So I need to look that I cannot have infinite terms to compile my solution. But if I have a look at the function over here, this is having power of x as 2 and power of y as 1. This d dash means derivative with respect to y. I have already discussed that this means derivative with respect to y. So when I apply this d dash in the numerator on this function x square y, then after the first derivative, since y is having power as 1, after the first derivative, the higher order derivatives will become 0. That means from this particular term, I will get 0 because d dash square will be there in the numerator. So hence the higher order derivative terms are of no use to me. So I will write only the first term, that is 1, and I will write only the second term, that is 2d dash upon d. I will write only 2 terms and remaining terms are being neglected. So when I apply these terms, then this expression 1 upon d cube plus 2d dash upon d plus 3x square y when applied, this 3 is constant, so it comes outside. I have written it over here. Then this 1 on being applied to x square y gives me x square y, and this 2 by d applied 2d dash upon d on being applied to x square y will give me 2 by d applied to x square, because derivative of y is being considered, so x will be considered as constant over here. So now to solve this, I need to, this 1 upon d means is actually equivalent to integration with respect to of any applied to any function. This means if I say apply it to x square, then this means integration of x square with respect to x. So integration of x square with respect to x give me x cube by 3. So I get 2 by 3 x cube as my value. This should be cube. Okay. So now further, this entire expression, if I solve this 1 upon d cube, if it is applied, so 1 upon d cube applied to x square y, y will be considered as constant. This gives me y integration 3 times of x square. So that means I will be having y x cube upon 3, integration left 2 times, then I will be having y integration of x4 upon 3 into 4, and in the end I will be having y x5 upon 3 into 4 into 5, and since I was having 3 outside, so on being multiplied by 3, this if it is 3 upon d cube applied to x square y, I will get x to the power 5 y divided by 20. So this expression I am having like this. Now in the same way, if I integrate 2 by 3 x cube with respect to x 3 times, I will get x to the power 6 upon 60, and hence my pi becomes 1 upon 60 3x to the power 5 y plus x to the power 6. So this is my pi. Now z obviously will be a complete solution given by CF plus pi. So z will be taken as function of y plus x times function of y plus function of y plus 2x. This was my CF, and pi was 1 by 60 3x to the power 5 y plus x to the power 6. So this is the way I am solving my second case pi questions. Now proceeding to the next case. So general method, this method is applicable to any kind of function, be it any kind of function. It could be an exponential function, a combination of algebraic, exponential or logarithmic, or any kind of a function. So how to proceed for this for this case if it is a general method? So let us consider an example. Suppose we have to solve d square minus dd dash minus 2d dash square z equal to y minus 1 e to the power x. Now we cannot apply case 1, it is not of the form ax plus by function. If it would have been only y minus 1, we could have, but since it is having e to the power x also, we cannot use case 1. Also it is not of the form of case 2, x to the power m y to the power n, hence general case will be applied. So to solve, first of all we will write down the auxiliary equation as m square minus m minus 2 equal to 0 by replacing d with m and d dash with 1, and we get m equal to 2 and minus 1. Complementary function is given by then y function of y plus 2x plus function of y minus x. So we have distinct roots, that is why we have considered the first case. So this is my complementary function part corresponding to the value of m as 2. This is my complementary function part corresponding to the value of m as -1. Now about particular integral. So to equate particular integral, this expression 1 upon d square minus dt dash minus 2d dash square applied to y minus 1 e to the power x, we will have to factorize this. So this denominator of d square minus dd dash minus 2d dash square is factored into two segments. One factor is d plus d dash, another factor is d minus 2d dash. So we have two factors. Now we will apply each of the factors one by one. So first of all, I am applying the factor 1 upon d minus 2d dash. Here this factor can be written in the form d plus m d dash, where m is -2. So therefore what I will do, I will replace y with c minus 2x. That means the process is we will replace y with c some constant plus mx. This m is the value of the factor, value of m we are considering in the factor, like in this case we are considering m as -2. So y minus 1 was my function. So instead of y, I have replaced y with c minus 2x. -1 e to the power x, integration, since this is linear, the derivative power is 1 here. So I will integrate 1 times. So integration e to the power x dx we are getting. On integration, first part, integration of e to the power x will remain e to the power x. Then minus derivative of c minus 2x minus 1 will be -2. It is like this. Integration of c minus 2x minus 1 e to the power x dx. This is equal to c minus 2x minus 1 integration of e to the power x dx minus integration of derivative of c minus 2x minus 1 into the integration of e to the power x dx, and this whole will be again integrated with respect to x. So we are having this value to be equal to c minus 2x minus 1 e to the power x minus the derivative of this function will be -2 e to the power x dx, and this gives me this integral value. So I am having this integration which can be seen written over here. Now this minus becomes plus, so I am having c minus 2x plus 1 into e to the power x. So this c minus 2x I have already considered as y in the starting. This is my y. So this c minus 2x will again be replaced by y. So this is again replaced by y, and again we are having one more factor left over here to be applied. So this becomes y plus 1 applied to e to the power x. So again we will proceed as we have just proceeded. We will replace this y by some constant plus mx, but this m this time will be taken from this factor d plus d dash. So if I write d plus d dash, can I write it as d plus 1 into d dash, and therefore I get m equal to 1. So m equal to 1 gives me y as c plus x. So now if I apply this factor d minus plus d dash on y plus 1 e to the power x, I need to replace y with c plus x. So let us have a look. So this factor I am solving. This, as I discussed, y is being replaced with c plus x. So this y is replaced with c plus x plus 1 e to the power x. Again we take the integration of this entire function. So as in the previous case, the integration will be c plus x plus 1 integration e to the power x dx minus integration of derivative of the expression c plus x plus 1, then integration of e to the power x will be e to the power x though, and this entire value will be again integrated with respect to x. So I am having c plus x plus 1 minus 1 into e to the power x is equal to c plus x e to the power x. Again we will resubstitute back c plus x equal to y. So on substituting c plus x over here, I get y e to the power x as my answer. That is my pi. This is my pi. And therefore complete solution will be given by complementary function plus particular integral, and that will be considered as z equal to function of y plus 2x plus function of y minus x plus y e to the power x. So we can see that there are 3 cases. So as per the need, we can consider my pi and cf accordingly, and complete solution can be found to homogeneous linear partial differential equation with constant coefficients. Thank you.